Hi, Richard Chase here, and we're starting a new batch of programming shows here. On Wednesdays I'll be bringing video from the Cascade Model Helicopter Club, some kind of a clinic from one of the experts down there. Thursday we'll have helicopter mechanic. Friday we'll have advanced helicopter flight school. And Saturday we'll have the live show from Performance RC Hobbies. Okay, now
girls,
I have a XC450 here
mine.
that has bent shaft, and I'm going to repair that and show you guys how to do that here. But what I really want to talk about on this very first ground school mechanics class is how does a blade create lift, or how does a wing create lift? And there's many explanations out there that never really seem to make very much sense to me. Not too long ago in Model Aviation magazine, they had a great article about how a wing creates lift. And all of a sudden it clicked to me, I get it now. And they dispelled the myth that it's the Bernoulli effect of the air goes faster over the wing and therefore it creates lift. Well, that's kind of a nebulous argument. I don't really see the connection there. It's going faster. But I do see this connection. I know that materials have a cohesionness because of their viscosity, and if you put water in a glass and it gets up to the top, it'll actually bulge over the top before it actually spills because the water molecules want to stick to each other. And in a similar way, air behaves on a little bit of a different scale because the air molecules are much smaller, but they do want to stick to each other. And what happens when air flies over a wing, this is my simulated wing here, when the air flows over a wing, it wants to stick to the surface of that wing, just like it kind of wanted to stick to the surface of the glass if you put too much water in it. And it will stick to the back of the wing. And by sticking to the back of the wing, it actually curves the flow of the air. Now, you can see that with a spoon. You can do that yourself. Take a spoon, take it over to the faucet and run some water. Don't run it so there's bubbles in it because that creates turbulence in the water, and we want a nice smooth laminar flow. So run the water with no bubbles in it, and then put the spoon up next to it. And you'll see the water will cling to the spoon. It will bend around the back of the spoon, and it will go this way. So that is really what's creating lift. It's this Coanda effect.
You heard it here.
The Coanda effect causes the air to stick to the back of the wing, and then it changes its direction, kind of.
So he's not all wrong, but this nebulous Bernoulli thing does have something actually to do with lift, which is kind of what we're about to embark on. And so there is a thing called a Coanda effect. It is basically the redirection of thrust that gives a push in a certain direction, and maybe we'll talk a little bit about that. But what we'll talk about now is our external flows. Before I was going to do that, I was going to just chat briefly about where we are in the class. Let me see if I can do this. Yeah, it doesn't show the whole thing, so anyway. Don't need that. Well, it's fine. So the presentations dates are coming up, which not until I think the first presentations are the 5th of December. So it's the week after Thanksgiving. So the due date was the 23rd, which is I guess the Friday after Thanksgiving. There's no particular reason for it to be that date. So I think we will change it from the 23rd, which is a Friday, 24th to the 28th, which is the following Wednesday. So the Wednesday after you get back from classes. It really isn't such an onerous deal. It's a 3-minute presentation. We've talked about it early on in class as to what it should be. I think it should be some interesting idea. You've already chosen the idea. I think you can illustrate it with some kind of embedded movie. It's always interesting. And it should be a hypothesis as to why it worked, and then some simple calculations to be able to make the case why the hypothesis is either true or not true, basically. So you saw some very quick examples of those with the water being held in the upside-down container with the grid, and the other one, which I thought was an interesting one, was how you can tell immediately in looking at movies when a model boat is being used in heavy seas versus a real boat. Based on the scaling of it and also surface tension. which are the two things. So there are some interesting things to do. So that is, so I guess they'll be due, there is an open Dropbox now on Angel, and I think it's going to be the 28th, which is the Wednesday. And so the idea is to have them all there so that when you make the presentation, we can just open Angel and we can open up the individual PowerPoint files immediately rather than people messing around with thumb drives. Because to do the 40 groups that we have in 4 periods, we need 10 per period. In a 50-minute period, you basically have 5 minutes. So a minute to set up, 3 minutes to talk about it, and then 1 minute to tear down and for questions if you have any. So that's kind of where we are. Don't make the mistake of needing 7 slides. You don't. One slide with a bunch of stuff on it densely, I think, is perhaps the best way to go. So anyway, so you've made many presentations in your lifetime before. So I think the presentations will start on the Wednesday the 5th. So it'll be Wednesday, Friday, Monday, Wednesday. The following Friday is the last day of classes. We'll have a review session if we haven't done it before for the final. The third midterm is on Monday the 3rd, which is, again, the week after you're back from Thanksgiving. And so, is there any reason, I haven't asked for a room for it yet, is there any reason for it not to be on the 3rd versus the 4th, which is a Tuesday, or no reason one way or the other? Okay. So, well, I'll ask for a room for the 3rd. It's another test. It's the, apparently when I put my finger across here, everyone can hear what I say anyway. But, so it's 3 questions. They are from the areas of energy equation, dimensional analysis, and pipe flow. And so there is an energy equation. I would encourage you to look at flow nets, for instance. There is a question on both dimensional analysis and on pipe flow, and you may remember that for each of those, we went through some questions in class. So we went off reservation for those, so you might want to look at those. So I'm sure you yeah. You didn't hear it? No. Oh, you can yell from there. 3 questions. You might look at flow nets. You got it? Got feedback? You might look at flow nets, and you might look at things. Yeah. So when you teach a class multiple times, it's nice to kind of do some things like we do. JetLev has been starring in our attractions lately, and you might remember some stuff we did with that. So have a look at the things that we've done, if you like, off reservation. You know, not going through the notes, but the stuff that's been scribbled on those little side pads that we've done. So we've done a couple of decent-sized examples on dimensional analysis and also on pipe flow in those. So I'd have a look at those. So that's so right now 3 questions and still an hour and a half. No real bonus points yet, but I haven't quite figured out that. I'm waiting for Lucy's comments on that. And I did monetize the last 2 videos. So for week 11, I'd be kind of interested when you look at them. If you do look at them, there are counts, I guess, of hits. So I think the other ones, just before the exam, there are about 40 views, I guess, for each of the YouTube movies. The movies are only now on YouTube. I did put them on my account before, but now they're on YouTube exclusively, and I do that just because it's easy, and because I can actually see how many people actually visit them. So I think just before the midterm, the stuff running up to that had about 40 views apiece. And then the review session had about 140 or so. So it's just kind of interesting. So I did monetize them. So the idea of the monetization is that if we make some money on that, perhaps we'll put that behind a bar at the end of the semester if anyone wants to go and utilize that. Woo! And so I'm not sure. It might buy a soda for one person. I'm not sure. But I have no idea what to expect from it. Okay? And that's about it. So, any questions for me as we go down the pike? So we've covered a lot of ground so far, and so I applaud you for hanging with us for this. What we're going to talk about today is external flows. It's not all that different from the stuff that we've done with pipe flows, where you have some kind of energy loss in the system between the flow pressure upstream and the flow pressure downstream. That flow pressure, we've done the calculation already. If you look at being able to evaluate that change in pressure between the upstream and downstream locations, that has to be the shear force which is applied on the water, and it would also be the shear force you'd have to apply to keep that pipe in place as well. And so the interesting thing about external flows is that typically it's, instead of being confined in the pipe, the expressions that we deal with are exactly the same as when we've dealt with pipe flow. But we're interested more in, less in the drag in terms of what that affects the flow rate, and more in terms of what the forces are on the structure and how we use that. So the forces on the structure might be drag or lift. Drag, for instance, on a car, because the drag force that you apply on a car by the air flowing past it is the force you have to apply to push it along the road. And so if you multiply the drag force by its velocity, you get the power that you have to consume to get over that force. Likewise for an airfoil, we're looking at this guy here, talking about an airfoil, whether it's a rotary wing, as in a helicopter. He's apparently the president of the helicopter club somewhere, the model helicopter club. You get lift and drag on wings, and that, of course, is the mechanism by which planes fly. If you look at forces on structures, I mentioned the other time, Alan Davenport was a professor at University of Western Ontario, which became kind of a world-renowned place to do wind tunnel studies on downtowns of cities, to be able to look at the forces on structures, new structures that you might build in terms of wind forces, which of course are affected by the other buildings around them. And so you make a wind model and you scale the experiments to be able to figure out exactly what those forces might be, whether the wind will knock the windows out, whether the people walking in the canyons at the base of those buildings will get blown down the street, etc. And so experimentation is a big part of some of this work. And so in terms of looking at external flows, we will kind of look at the parallels, if you like, between what we've done for pipe flows and for, we'll draw the parallels between pipe flows and what we've done. So if you'll indulge me for a moment, what I wanted to do was to basically kind of look at where we've come from and be able to tie it kind of all together, if I can. So we are officially now in week 12. I guess it's not 12-1, it's the second period, so, but we're one behind, so we're talking about external flows. And so, indulge me. Where have we come from? So you should be happy with yourselves. We've covered a lot of ground in this class. You know, we're on page 300 and something of these handwritten notes. We're on chapter 11 or something in the book, and so we've covered a lot of ground. But if you go back to where we started from, if you remember what we were doing 12 weeks ago, then everything that we initiated started out from Newton's second law. And if you remember, when we talked about forces on structures, we ended up deriving on a little differential brick an equation, which you might remember, or you might not, which was this, which is basically saying what the pressure distribution is as a function of accelerations due to gravity or accelerations due to moving up in an elevator, if you like. And if you recall, we used this to get, for a static fluid, this expression, right, which is this term here, which says that pressure changes linearly as you go down within a fluid. And ultimately, this also gave us what? This gave us the pressure is equal to P0 plus the depth times the unit weight, right? That's basically that expression. We use this expression to kind of derive another equation when the fluid wasn't static. So this is static. We used it to derive another expression, and you will recognize this other expression. plus or minus a term HP equals constant. So you'll recognize this for sure. This, of course, right, remember this, acceleration is what? It's change in velocity with time, which is the same as change in velocity with location and location with time, which is equal to velocity dv dz. Yeah, so this should be z, right? My z's and t's look too close to each other, which is the same as d dz v squared over 2. Right? So it doesn't matter about that, but this term here becomes this. You know that. So pressure head, elevation head, velocity head, and the fluid loss within the system. So if we call this pressure, if we call this elevation head, if we call this inertia, and if we call this viscous loss, you remember we did a few things with these. We looked at, for instance, so this is this course in 10 minutes or less, basically. We looked at the ratio of the inertial forces to the viscous forces. And so this was inertial to viscous forces. And that came out to be a number which was a velocity, a density, a length scale, and a viscosity, viscous forces on the bottom. And we said that was kind of important in some of the things that we deal with. We also looked at, and so this is the important one, inertial forces are kind of the important one. We looked at the ratio of inertial forces to elevation forces, or to gravity. This could be gravity, I guess. So we had another number called the Froude number, which was the ratio of inertial forces to elevation. I should probably have called the elevation forces gravity forces, which gives us a number which is a velocity divided by gravity and some length scale also, which happens to be kind of also the wave speed. So it's basically the speed of this is the velocity of a bow wave from a ship, the natural velocity, the celerity wave will travel. And that was this. And we also looked at the ratio of the inertial forces and the pressure forces. And that's an important one to us because this is what we've referred to as the Euler number. It is the ratio of the pressure forces to the inertial forces. And you'll recognize the number. It comes out to be something like a fluid pressure divided by, what is it? Density of the fluid, the velocity squared, just that. And we can also write this as a force. If we call the force P, uppercase P instead of a pressure, then it's density times the velocity squared times an area. So force over area is just equal to pressure, right? That's all I'm doing. So those were kind of three important forces that came out. So this is basically what we've done in 10 weeks in a nutshell. We used Newton's second law. We got fluid pressures in a static body. We used that to get an equation which we account to Bernoulli. If we add either pump losses or pump head or pump losses to the system, then it's got, instead of being inviscid, we're able to look at the viscous losses in the system, and we end up with three important non-dimensional parameters which describe our behavior. And so the reason for going through this is that now what we can do with these, if I can take this, is that you remember when we talked about pipe flow, we looked at flow over some length with some diameter, some velocity into the system, some pressure, which is applied on here, which is different from the downstream pressure, and we had the flow through the system. So this is what we referred to as an internal flow. And we could also look at the same, we made the point when we talked about this, that you could also look at the same thing in profile. I won't draw it in perspective, but imagine if this pipe was just a closed pipe. So you close the ends and you flow past it, and you get this kind of flow. This is an external flow, and this is velocity as it goes past. There would be a pressure applied here. There'd probably be shear forces applied on here as well, which we won't care too much about for now, as drag. This stuff goes either side and down here. And again, this would have the same kind of characteristic dimensions that would describe this behavior. And, you know, this is a pressure, this is some kind of area here if you wanted to. So what links, the question is, what links these two behaviors? They're very similar. One happens to be flow inside a pipe, and the other one happens to be flow outside a pipe. Of course, we don't really worry about that too much. If you think about the pipe as, instead of being a pipe, as being the shape of an airfoil, then we would be interested in what the forces are that are applied on this. And so what we dealt with was that this magnitude of the power here, I suppose you could also write this as the head loss in the system, right? They're both equivalent components. And so what do we have? We have the head loss from pipe flow is equal to what? It's equal to friction factor, some length of diameter of the pipe, and the velocity head, v squared over 2g. And this also is equal to what? The units of this are equal to the pressure applied on this surface, the difference in pressure between the upstream location and the downstream location. It would be the same here, right? There's some pressure here due to stagnation, and you'd have a lower pressure at the back side, so you'd have to apply physically, a force would have to be applied to this to be able to keep it in place. And so this is a pressure divided by a unit weight of fluid. And so what we could do is we could, instead of writing this as that, we could write it as this, right? That's just the same material. And so these are just really equivalent dimensions, if you like. But what we could think about this is we could rearrange this in some way by looking at these two relationships, right? We get rid of g on both sides. And what we could do is we could divide both sides by v squared over 2. And if we do that, we end up with what? P over rho v squared times a half is equal to friction factor, length over diameter, and of course dividing by v squared over 2 just gets rid of that component. And so this is kind of important, right? Because you've seen each of these expressions before, and it basically says this. We've looked at our Moody charts, and our Moody charts say that as a function of Reynolds number, you know, this would be 10 to the 3, 10 to the 4, 10 to the 5, right? Reynolds number, you remember that, of course. It's velocity, density, some length scale. Perhaps we should use d, since we've used that over viscosity. And a value of friction factor. And so the numbers that we've had are, you know, this is 64 over Reynolds number. And we have all these numbers here that are equal to different values of the relative roughness is low, and the relative roughness is high, relative numbers. And this is what friction factor has been. So friction factor, if you think about it, well, we can multiply by some constant, whatever that is. We're saying that this is equal to a pressure divided by a half rho half v squared. This is an Euler number, right? What we've called our Euler number. And so all it serves to define is the fact that there's a direct correspondence between internal and external flows. It's just that we're interested in different things. In internal flows, we're typically interested in how much fluid can you push down this pipe, and we want to know what the frictional resistance is to be able to modify our equations to be able to calculate that. In external flows, well, having a wing in an airstream doesn't really modify the bulk flow of the air around it very much, but it puts a force on that. And typically what our interest is in figuring out exactly what the force is. And so what we're often interested in evaluating is not a pressure, but a force, which is a pressure divided by an area. and a half rho v squared. Right? So we've done nothing. This is a pressure, so this is newtons per meter squared. This is a force, this is in newtons, and this is in meters squared, some characteristic length. And this is still an Euler number, but this is called now a coefficient of drag or a coefficient of lift, because it allows us to be able to figure out exactly what the force is that we have to apply on the structure to react against the force which is being applied by the flow around it. And it depends on the velocity of the fluid that flows around it, the density of that fluid that flows around it, and some characteristic dimension squared, some area. So for an airfoil, it might be the area, the planiform area of the wing, the plane, the vertical view of the wing. For drag, it might be the frontal area of the wing as you're looking at it from the front of the plane, etc. But that's basically what we're attempting to do. So what we're trying to do for external flows is being able to figure out typically what the magnitude of this force is that you have to apply to the structure to be able to stop it from moving. And of course, if it's a force that you have to apply to a car to move it at 20 miles an hour, taking that force and multiplying it by the velocity gives you the power that you have to expend to be able to push it against the wind resistance. So that's kind of where we're going with this, okay? So, I guess, where are we? We'll see if we get to it, okay? So, the basic ideas are here. So there are only a couple of equations that we deal with for this. Let me also get this in full screen mode. And so typically what we would like to deal with is that if you look at, for want of a better geometry, some magnitude of a wing, we're interested in the drag force that we have to push against. We're interested in the lift force that we have to apply. And you can get these in a variety of different ways. We can get them by looking at the fluid pressures that are applied on the wing and the shear stresses due to viscosity and figure out exactly what these are. Or you could take your wing into a wind tunnel and you could physically flow fluid past them and measure those forces directly and then correlate them in some way. And we've already seen from what we just did that typically what we think the way to correlate those would be to be able to define them as either a coefficient of drag or a coefficient of lift versus a Reynolds number. And those typically will look like something. So that's basically what we're attempting to do. So you can do these things in a variety of different ways. We can measure them in the wind tunnel, in the laboratory. You could measure them in reality in the field if you wanted to. You could measure the forces on a flagpole as the wind blows at different velocities across it and figure out what the forces are that are applied onto it. You can do it if you know what the flow regime is around it in terms of the pressures and the shear stresses, and you can get those either from analytical solutions or from numerical solutions, and we'll look at some of those today. So that's basically the idea. So, external flows. We're interested mainly in the forces that are applied. The only thing that's different between lift and drag is it's a force that's applied on the structure. Lift is typically perpendicular, the force perpendicular to the airflow. Right? So on an airfoil, the air comes over the wind. Lift is the magnitude of the force perpendicular to that far field velocity. And in drag, it's a force aligned in the same direction as the flow. We're interested in it on a variety of structures, cars and buses. Obviously for fuel efficiency, the more streamlined the structure is, the better gas mileage you'll have. Of course, you want it to actually look nice as well. If people don't buy it and use it, then that's kind of a problem as well. I remember these the first Honda Civic hybrids that had these kind of cowls over the wheels, the first hybrids actually. I don't think were very successful because they were just so unusual that even though you gain by having no swirling airflows around the wheel wells, if people don't buy the car and don't want to use it, then it won't be a successful way to go ahead. So public acceptance is important. We'll do an example with an airfoil after we've talked about this. But the basic idea is that you can imagine that we're interested in being able to figure out what the magnitudes of these forces are. And lift and drag occur due to two effects. So there's one effect, so you could imagine, the easiest way to think about it actually is if we go to this picture here, right? So if you think about this, So if I'm getting hit by air in my chest, then the fact that the air is traveling at some velocity over here and at zero velocity on my chest means there's a force applied on me because we're killing the momentum of that fluid flow as it hits my chest. So there's a pressure drop, you multiply the pressure drop over the area of my body, and you have a force that's applied on me. And so in that case, the main force applied on me will be like this, right? A plate that's held vertically, you kill the velocity here as your stagnation point, the flow has to go around it, and therefore you take the pressure that's applied over this area, and you can calculate the magnitude of the force that you'd have to apply to react against this, which would be this uppercase P, to be able to resist that. Okay? So that's one source of the force that you'd have to resist. If you take that plate, or if maybe you have me lying down and then having something flow over the top of me, as if I'm dead on a mortuary slab, then the forces are going to be different, and they're for a different reason. And the forces then would be because there's some kind of shear applied along the length of my body, because the velocity where it sticks onto this surface is zero, and as you get progressively further away from the surface, it's actually at the far field velocity u. But obviously here, this value here is going to be a change in velocity in the x direction, and it changes with y, right? So there's a high gradient here. This gradient here, if you draw it, right? So if you imagine this as being ux, it's zero at this point here, and it curves off here. This is the y direction. So in other words, at this point here, there's a gradient dux dy, which is quite large, potentially. And we know from Newton's law of viscosity that if you multiply that by this, it gives you something you've already seen, right? And so the point is that at this location, there's some kind of shear force applied on this boundary, and to be able to hold that plate in place, you'd have to apply a force on that plate, and that plate, I guess, would be a force equal to S, which would be equal to 2 times the shear stress times the area of the plate, right? Top and bottom. So the plate has an area, it's top and bottom, it has an average shear stress on it, and you can get the force that's applied on that. So all by way of saying that there are 2 sources of this force that's applied to us. The pressure hitting my chest due to killing the velocity, stagnation, and also the effect of shear. Obviously, in both of these examples, there'd be kind of an effect of shear around here, right? There'd be a small amount of shear you could imagine is being applied here, but the relative magnitude of this compared to the pressure is probably going to be small. And likewise, you're killing the velocity here, and there'd be a stagnation point here, so there'd be a pressure here, and a very small area, so there'd also be a pressure force as well. But in each of these cases, this would be mainly shear, this would be mainly due to stagnation. And so you see that in each of these expressions here, in that if we wanted to calculate incrementally what the force is as you go around this airfoil, we can calculate what the contribution is due to the pressure over an area of this that's arranged in the direction in which we're interested in. So in this particular case, the x direction is in this direction. And so if you're calculating what the force is in that direction, this would be Fx, resolving. And so the force in that direction would be the pressure that's applied over an area of the airfoil, corrected for the angle in which it's applied itself, right? So you have a pressure that's applied here. You're interested in the component which is in, it'd be this one, right? This would be it here. So this is the pressure applied on the face of this here. It's over some area which is just some length dA. So the total force is going to be this pressure times the area. And if you want to correct it for the component that's pointing in this direction, it's just going to be PdA times cosine theta, which is this term. Well, it's this term here, right? Likewise, at that same point, there's a flow due to the shear stress. The shear stress is equal to tau W. It's also applied over the area. And so if you want to calculate the component of that which is in this direction, F, it's just going to be the shear stress times the area. So this would be our total force, if you like, that we had on the previous slide, and multiplied by its component in this direction. So that's all it is. So we're looking at each of those components in the x direction. This is an increment of the force. If you sum it up for all the different points around this airfoil, you have them all together. You just do it by integrating. So you integrate both sides, nothing more than that, and you end up with this expression. So the drag force that's applied to this due to both of these components, this hitting me in the chest and killing the velocity, this squiggling past me and dragging me just by the shear force due to the viscosity of the fluid are both added up to get that. And so that's really where that comes from. If you look at an airfoil, you can kind of decompose it down into those two components as well, right? You have an air velocity coming in, it hits the airfoil, it's a stagnation point, the flow then has to go around here. So you'd expect the pressure to be here, large, because it's going from U here to 0 at this point. So that magnitude should be about delta P over gamma should be about equal to what? A half V squared over G, right? Just because of that. And as you went around here, it would diminish. And so this green stuff is the force that's acting as a positive pressure. And on the top side, the red stuff is the stuff which is a negative pressure relative to the ambient pressure. So this would be below the pressure here. So this would be P external. The green is P greater than PE, and the red is P less than PE. That's all. And of course, that's what you want on a wing, is right. You'd like this to be less than the external force, because now, if you look at the net force acting upwards, this is a negative pressure times an area. This is a positive pressure acting upwards times an area, and it would be a net upwards force, lift in other words. The component of this force acting downstream is going to give you the magnitude of D. So I guess actually D would be the force that is acting due to the summation of these in this direction. L would be the force that's acting upwards. And it's the same geometry as before. A positive force is one that's in the positive x-axis direction. A positive lift is positive in the y-axis direction. Nothing more than that. Okay? And so it's just to reinforce the idea that on a wing, you not only have lift, which is what you're interested in, but you also have some kind of drag as well. You'd like to maximize lift, and you'd like to minimize drag, because obviously you have to push against drag. And to make the point that both lift and drag are due to two effects. One is due to the pressure influence that causes both lift and drag in this case. And obviously in this case, maybe not obviously, certainly you could see that the shear stress has an effect on drag, but also there's a component of the shear stress acting vertically here, which would cause some form of lift. You don't know what the net effect would be, either positive or negative in that particular case, right? So you can do that. So if we wanted to, and if we knew the fluid pressures, and if we knew the shear stresses that act on the structure, we could calculate what the magnitude of these forces would be. And you can do that if you know what there are some solutions available, for instance, for plates and the boundary layers that develop around plates to be able to give you the velocities around here, so you can calculate what this gradient is, and you could just calculate what those integrals are from those straightforward solutions. Okay. So, and we won't do that right now. So the other thing that is, we mentioned before, that's typically done by maybe running models in wind tunnels. Oh, don't do it to me. I think it's just thinking. It's thinking for a long time. Well, so typically these expressions, well, it was there. Okay. Let's hope it. So this piece of software only runs on Windows, or the version I have only runs on Windows. So we'll see if how long it takes to let us in here. Okay. And so what you could do is you could try and figure out exactly what the magnitudes of the forces are that are applied on the structure. You could do it in a wind tunnel. You could use analytical solutions, or you could use some numerical models that allow you to do that as well. And let it think for itself. And those models would do something like this. Let's see if it is able to arrange itself. I guess you can see that. So this is just a model that has that solved Navier-Stokes equations. So we talked about Navier-Stokes equations. We didn't really do anything in detail to deal with them. But basically what, if you recall, we could write our momentum equation and we could write our continuity equations. Instead of using Reynolds transport theorem, we could write them on little cubes, differential cubes, and we come up with a series of equations that allow us to be able to solve problems of flow in fluids. And in this particular case, this would be an airfoil which has a fluid flowing around it. And to that fluid, what we would do is we would apply some velocities. So in this particular case, I guess I could go in here and do this. See if it'll do it. This merely takes this geometry, and what it does, it allows us to be able to put some kind of fluid properties in it. And you'll see that the fluid properties are of density. This is our dynamic viscosity. This is what we've called mu, and also forces that we apply within the system. It allows us to be able to put in boundary conditions, and the boundary conditions would be that on this upstream boundary here, of fluid going in, we have a velocity that comes in across that boundary, which is 1 meter a second. And we have a boundary condition as it goes out of the system of a prescribed pressure, which is just 0 ambient pressure. And we have boundary conditions on the surface of this airfoil, which would be no slip. So in other words, we're saying that the air that goes past this, or the fluid that goes past this, attaches itself on that wing, and it would be 0 velocity right on the wing boundary. But as you get further away from it, it would get up to the velocity of the fluid, which is kind of the ambient velocity within the system. And on this top boundary as well, we just have a slip boundary, which means that the velocity along here is basically 1 meter a second, just as it goes across here. So those are the boundary conditions that are set for this. And so the idea is that what we can do is we'd like to be able to solve for the flow system that goes through this. And so we have air coming across this blue boundary at 1 meter a second. We have the pressure here equal to 0 gauge pressure. We have a slip boundary condition so that the velocity along this red boundary and also the turquoise boundary on the bottom is also 1 meter a second to the left, to your right rather. And we have boundary conditions on this whole airfoil. These are just arrows that join each other, that are 0. And so we try and solve that system of equations. And so what we end up doing is we divide it up into a whole bunch of little triangles. And basically what those triangles allow us to do are to be I can't draw on the picture directly, but I can try drawing on here. So what those triangles are, if you remember when we talked about Navier-Stokes, we had a flow into the system and a flow out. We could solve, if you remember, what was it? We solved our moment of momentum equation, which was sum of forces in the x is equal to velocity times the mass flow rate. We had sum of forces in the y direction equal the velocity times the mass flow rate. And we had the mass conservation equation, which was m dot equals 0. Right? And so you could do these using Reynolds transport theorem, or you could do them on this little cube, actually a square in 2 dimensions, right? X and Y, to be able to define that. So we have 3 equations, and instead of doing that on that particular geometry, the geometry we use here is we divide this whole flow system up into a whole bunch of elements. Each of these elements is basically the same as this. We have 3 equations written, and at each of these nodes, we have a velocity in the x direction, a velocity in the y direction, and a fluid pressure. And so we have 3 equations, we have 3 unknowns, 2 velocities and a fluid pressure, and we're able to solve for those in the system. So that's basically all this method does. It's called finite element method. And if you run it, it runs relatively quickly. It basically solves a whole bunch of, it sets up an equation, 3 equations for every single point within this grid, and then it solves simultaneously to get a solution that basically fits the boundary conditions. Nothing other than that. And so what I'm going to do is I'm going to run it for a value of this viscosity, which is equal to 1, viscosity equal to 0.1, a viscosity equal to 0.01, and also 0.001. If I do it for the next one, it doesn't solve it because it's a very high Reynolds number. It doesn't solve it easily. And as a result of this, what it does is it comes up with a flow field, which is shown here. And so this is the flow field that it solves for. This length of this arrow would be 1 meter a second coming in here. It's 1 meter a second going out. But as it goes around this airfoil, if we go into this, I can do it for different, this is for different viscosities. You see, yeah, actually you see, right? So these are streak lines that show the flow pattern. And you see it goes above here. I guess you can actually probably do this as well, right? Does that work? You see the streamlines as go here. This is, the colors are pressure contours. So you get a high pressure where it stagnates at the tip. You see it divides flow. This would be a stagnation point here. There isn't, where you basically have the streamlines go either side. This is a relatively low velocity compared to this. This would be close to 1 meter a second, right? Out away from the wing you'd expect. And it goes relatively small magnitude here. At this point here, the velocity along the width of the wing would be 0, just because of the boundary condition that we've applied. And so I think we can look at that if we do something like this. Didn't want that. If we look at drawing a cross-section that goes from 0, 0 is the center of the airfoil. X1 is the top of the box. Yeah, okay, so this is it. Okay. Well, it looks different from what I remember it from last night. Anyway, that's fine. So if you look at where this is, so it hasn't, okay, that's because it's there. I don't want to, so let's not do that. Let's do, so I want to go between the center of the airfoil and above it. So I want 0, 1, right? And it will show it on that figure. Yeah, that's better. So the location of this is this, right? So we're drawing a section of the velocities now that go across from the wing, and that's what these are. And so this is the portion that is right on the edge of the wing. You see the velocities are 0. And as you go further upwards, vertically above it, then you see a couple of different behaviors. First of all, you see for sure that this is the velocity here versus distance. And so if you like, if you measure, this is change in velocity with length away from the wing. So this is dv dy in the viscosity term. And you see that this term is 0 velocity at the wing, and it goes to the far field velocity. Actually, it should be equal to about 1, right? As you get further away, it's a bit larger than that. It shouldn't be. And these are values for different values of viscosity. And so what that's saying is that in each case, we're using the same value of the flow rate coming in. The density of the fluid is 1 kilogram per cubic meter, which is basically air. The wing size is the same in each case. And so by changing the viscosity, what we're doing is we're changing the Reynolds number. So these are the magnitudes for different Reynolds number flows. And if you see that here, if we just switch through these for the different magnitudes of the Reynolds number, so the viscosities are equal to 1. So the Reynolds number is proportional to, well, what is the Reynolds number for this? It's density, velocity, and characteristic length divided by viscosity. Density is 1. The airfoil length, wing length is 1. The velocity is 1. So it's 1 divided by the viscosity. So this would be a Reynolds number of 1. This would be 10 100, 1,000 for each of these, right? So at Reynolds number of 1, it looks like this. A Reynolds number of 10, it looks like this. Any difference? 100. Right? You see some separation occurring here. And in this case here, you see these vortices in the back. So these are just 3 snapshots of what the flow fields are at different Reynolds numbers in the system. And if we wanted to, maybe we'll save it for next time, the other thing that we can do with this is we can just merely go and we can calculate, for instance, we can calculate the magnitudes of the total forces in the x direction, which I guess would be drag in this case, which would be the drag that's applied to this is 0.107 newtons per meter into the page for that particular Reynolds number. And so the bottom line is that you can calculate the magnitudes of the fluid pressures and the shear stresses that are applied on this. You can use that to be able to figure out exactly what the forces would be applied on that structure, and from that you can use that to calculate the magnitudes of the lift or drag that are applied on the system.